missile you have just seen is the Air Force's X-17, one of the fastest instrumented vehicles ever flown in this country. The complete X-17 is a three-stage missile. It's taller than a four-story building, and it weighs approximately 6 tons. This is a model of the X-17. It has saved the government millions of dollars, and more important, many valuable months of time. When the Air Force began development of long-range ballistic missiles, such as the Atlas and the Thor, we were certain we could solve every problem except one, the problem of re-entry. Now, what happens when a long-range missile traveling at 14 times the speed of sound dives from space into the Earth's atmosphere? Would it flame and disintegrate like a meteor? Or would it be possible to develop materials which could withstand this extreme heat? To find the answer, we needed a special, inexpensive missile which could re-enter the atmosphere faster than any yet developed. This, then, is the X-17 story.
The path of an intercontinental ballistic missile takes it far outside the Earth's atmosphere. After blasting away from the launch pad, it surges to fantastic heights. In the void of outer space, it hurtles toward the distant continent at tremendous speeds. But what will happen when the warhead of the missile, traveling as fast as a meteor, re-enters the dense air surrounding the Earth? Like a meteor, will it blaze to a white-hot mass and disintegrate in a shower of flame? Or can it be made to hold its lethal cargo until it reaches the target far below? The answer was critical. It had to be found early in the program. The only way to find it was by means of a special test vehicle which could make or simulate the blazing re-entry of a full-scale ballistic missile. The Air Research and Development Command of the Air Force was assigned the job of producing both the research missile and a nose cone which would withstand the tremendous temperatures and pressures. In accordance with Air Force policy, the actual work would be turned over to private industry, with the Ballistics Missile Division of the Air Force managing and coordinating the far-reaching activities. In this way, the vast resources and experience of America's science and industry could be concentrated on the problem. Subsequently, Lockheed Aircraft's Missile Systems Division was awarded a contract to build such a missile. The missile consists of 3 stages, with the 3rd stage carrying the test nose cone. At launch, the 1st stage rocket will fire. 2 additional spin rockets will rotate the missile, much as a bullet is spin stabilized for the rifling in a gun barrel. After launch, the missile will climb high beyond the atmosphere into the airless void of space. Without air to act on the tail fins, the missile remains in an upright position. Reaching its peak, it then begins the long fall back toward Earth, gathering speed as it falls. When it re-enters the atmosphere, the flow of air on the tail fins slowly turns the missile to a nose-down position. By now, it will be falling at supersonic speeds. 90,000 feet above the surface of the Earth, the 2nd stage rocket fires. This ejects the now useless 1st stage and drives the missile toward the Earth at even greater velocities, creating a powerful shock wave ahead of the hurtling nose cone. But even this super speed is not enough. Now the final stage fires, forcing the nose cone to velocities as great as 14 times the speed of sound. Sensitive instruments inside the nose cone faithfully measure every degree of heat, every ounce of pressure. On the ground below, radio signals from the missile will be received, preserving the valuable data attainable in no other way, recording the secrets of space until the missile hurls itself to destruction. This was the work that must be done. But to design and build a re-entry test vehicle which could do the work was not going to be easy. It would not only have to be capable of performance in unexplored regions, but to complicate the problem, it would have to be designed, built, and operating in an unbelievably short time. This seemingly insurmountable task was broken down into sections to utilize the specialized knowledge of many industries, each feeding information to the other. Then, long before the construction of the missile could begin, the flight problem must be analyzed by electronic brains, such as the UNIVAC scientific computer. The elements of weight, total rocket impulse, Mach numbers of the various stages, friction of the air, dispersion, altitudes, temperatures, in short, thousands of quantities which could affect the flight of the missile had to be considered. This wealth of information was used by Lockheed Missile Systems Division in conjunction with their own vast research program to design the first X-17 test vehicle. To support the construction program, a number of smaller test vehicles were designed and fabricated, then tested at the Holloman Air Development Center in New Mexico. One of these was designed to investigate separation characteristics, to see whether the various stages could be separated on schedule while yet withstanding the terrific strains produced by hypersonic speeds at extreme altitudes. These test flights proved the basic design to be sound. At the facilities of rocket motor manufacturers, the necessary spin rockets and igniters were prepared. Other concerns were manufacturing what were then the world's largest solid propellant rockets. Prior to use on the missile, these rocket motors were fired in tests, eventually proving so successful that they're now being used on other missiles. But the managing of a complete missile system does not stop with the building of a rocket. Among other things, a method of launching had to be found. This involved creating a new type of mobile carrier for raising the missile to the correct launch position. All of this vast development program was geared to one purpose. What kind of a nose cone could be used to penetrate the atmosphere at hypersonic speeds? Should it be an aerodynamically clean, sharp point as utilized on airplanes? After careful analysis, this did not seem feasible. Incongruous as it seems, it was at last determined mathematically that a relatively blunt shape would be the most suitable. To put this theory to the test, complete nose cones were constructed. Copper was used for the material, as it has the ability to quickly absorb great amounts of heat. The interior of the nose was fitted with sub-miniature instruments to measure temperature and pressure. When the nose cones were completed, they were plated with a thin coating of nickel, then buffed and polished to a finish many times smoother than the most expensive crystal. The timing of the entire program was extremely critical. It was a tremendous task to coordinate developments from all over the nation so that every phase of the complex test program would be ready at exactly the same time. But a carefully coordinated schedule was followed. And early one morning at the Air Force Missile Test Center in Florida, all parts were brought together for the supreme test. The first nose cone was mounted on the missile. With all checkouts complete, the strongback raised the missile, and it was aligned for the correct launch angle. An explosive destruct charge was carefully placed inside. This was for the purpose of deliberately destroying the missile should a malfunction occur in flight. Within the concrete blockhouse, preparations were being made for the firing sequence, the engineers tensely performing their routine checks. Timers were cautiously set and recorders set in motion. The range safety officer watched carefully, ready to destroy the missile should it be necessary. At last, everything was ready, and the missile waited, quietly, patiently.
29, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, fire.
something is wrong. Unknown to the men inside the blockhouse, one of the fins has struck the launch platform. Instantly, the missile is out of alignment and begins to veer off course. The spinning missile fights to maintain its heading, but the fin is bent too far. On the ground, the tracking cameras follow the flight, memorizing what is happening to the bird. By now, the missile is definitely erratic and heading off range. Having no alternative, the range safety officer presses the destruct button. 70,000 feet in the air and traveling 5 times the speed of sound, the missile disintegrates in a thunderous blast, the supersonic speed ripping the pieces to shreds. The life of the missile is ended, but it has not died in vain, for it has left a wealth of knowledge. Safely on the ground, stored in the memory of tape sensor units, are the facts that passed through the electronic brain of the missile. And recorded on film is a graphic picture of the mission. Slow-motion films taken at the instant of launch proved that the spin rockets fired a fraction of a second too soon, causing the missile to rotate before it left the launcher. Here, a fraction of a second spelled the difference between success and failure. But had the mission really been a failure? No, not when information had been returned, which would save missiles many times more costly. And soon another missile is ready for launch. This time it has a built-in safety feature, which will prevent a similar malfunction. As time for the launch approaches, the work of preparing the missile goes forward tensely. The lethal destruct charge is gently placed inside. The men in the blockhouse continue their endless checking, watching the gauges and meters, which are their eyes and hands. Last-minute warnings are given, and the countdown begins. Out on the launch pad, the missile stands alone, awaiting the rocket blast that will carry it to destruction. For whether the flight is a success or a failure, it will be a one-way mission. It was made for one purpose, one supreme flight, and there can be no return.
3, 2, 1, 0.
Then it is gone, but only from the sight of man. On the ground, sensitive instruments are monitoring the pulse of the missile. At this moment, almost 100 miles in space, the missile is beginning its suicidal plunge toward Earth, driving itself to velocities of almost 10,000 miles per hour, probing a frontier unknown to man. Then it is over. The missile is gone. But invaluable research data has been obtained, moving man a step closer to solving the mystery of hypersonic re-entry. Other flights quickly followed, setting new records of achievement. Soon, a wealth of information began funneling into the hands of research scientists. Information which might have taken years to obtain at a staggering cost has been gathered in a few months and at a fraction of the estimated price.
The X-17 has accomplished its original mission and has now taken its place in our family of missiles. It is now available for immediate use, either as a far-reaching instrument of research or as a weapon for the defense of our nation. The X-17 missile, with the information obtained from its re-entry flights, has been turned over to the Navy and is now being used on their Polaris program. Missiles such as the Lockheed X-17 provide a constantly growing stream of knowledge, ensuring ultimate national supremacy in the new space frontier.